In this video, I'd like to show you in Mathematica or Wolfram Cloud how to plot two functions on one plot, and also to manipulate a function in a plot, sort of to have some parameter, and then we'll have a little slider that will allow you to sort of change the parameter and see the plot update. Okay. So for the example, I'm taking just a simple little wave function, an amplitude A times cosine of, I'll call it omega, just a W, times the time, plus P, I'll put in for a phase. I'm not doing any fancy symbols, sorry about that. So it's just defined, I just made up this name wave. I'm defining a function, so square brackets. I'm defining a function, so these strokes, or I'll just say underscore, and colon equals. And then if I enter that, shift enter. Now, when you're defining a function, that's a time that you don't get an out. So you're just defining something. So there's no out, there's just the in. Okay. And now we can plot that function. So I'm setting the parameter A to 1.2, W to 2.3, P to 0.7. I'm just making these things up. There's nothing particular about those values. And then I'm going to leave T as the variable and plot T from 0 to 10. So just this cosine doesn't start at the maximum because of the phase. Start somewhere in the middle of the cycle. Okay. Now here we are going to plot just sort of two functions at once. So we want to make a sort of, if you will, a list of functions, or a list, yes, a list of functions. So I have my curly bracket, and I have wave here at 1.2, 2.3, 0.7, and T, and comma, and then wave again, and this time 1.7. So I'm just changing the first parameter and leaving the other parameters the same, and of course the variable the same. And so again, it's just replace, compared to plot above of one function, I'm replacing this one function with a list, so curly brackets around two functions separated by commas. And then I've decided to give it a plot label to say that I want, then what I'm showing you here is that the amplitudes are different. And then just for, I don't know, completeness, I said, let's look at different frequencies. So here I put the amplitude to 1.2 for both of them, but made one frequency 2.3 and the other one 3.2, and plotted that. And then we see that that the blue is slower, that this, I don't know, amber color, orangey amber, is repeating more rapidly. And should probably learn how to make a legend, so maybe another time. And here it's a different phase, so 1.2, 2.3 for both of them, and now the phase is different. So let me do shift enter on that. So we have two equations with different phases. Okay, now I want to return to this different frequency one. And you see here sometimes, say around 8, these two waves are very close to each other, sort of close to being in sync. And down here at, say, close to 4, a little bit below 4, they're sort of doing the opposite. So if I were to add those two functions, they would be canceling around here at 4, and they'd be adding significantly here at 8. So that's what I have done here. And this is when you're adding two waves that have different frequencies, you're looking at a phenomenon in physics known as beats, that you have sort of this more complicated oscillating pattern, and then the sort of there's a fast oscillation, and then there's a slower oscillation on top of it known as the envelope. And so at 4 is where the envelope has its sort of minimum, and at close to 8 is where it has its maximum. And this came about because of the difference in frequencies. So they were going in and out of phase. They were doing the same thing, or they were doing opposite things. If they're doing opposite things, they cancel. If they're doing the same thing, they add. So the superposition is destructive here, they say, and constructive here. Okay. So now what I've done, so here is the repeat of what was above, the plot of one wave plus another wave. And t was my variable, and t I decided to take to 20 this time. But I've taken the second frequency, the second wave's frequency, instead of putting in, as I did above, a specific value of 3.2, I went back to making it a parameter. So I'll distinguish here the variable is what I'm going to plot over, and everything else is going to be the parameters, but I'm going to manipulate the one parameter. And so I had, again, here's what I had above, the plot. And then I added around that this manipulate. So I'm going to manipulate my plot. And I'm going to allow, I need like a range of manipulation. So I'm allowing the frequency of the second wave f to vary from 0.8 to 4. Again, I'm just making these things up on the fly. And then I added one more feature to this. So this was the lowest, the minimum f I'm allowing, the maximum f I'm allowing. And then, and that alone would give me this slide bar that allowed me to change f. But then I said, appearance, I said, was labeled, and that's going to allow me to see the value of f that I have at a particular instance. So shift enter, and I get my graph. Yes, okay. And here it chose to put the f at the minimum to start, but I can slide it. So we see here this sort of, the frequencies are different, 2.3 and 0.8, and we see this sort of some of the beat phenomena. Now I can slide. I can also use this plus. No, this plus, sorry. And you see the sort of sometimes big amplitude, sometimes small amplitude. And then the interesting thing happens when they get close. So I'm now close. Here's 2.3 and I'm at 1.98. So they're sort of close. And then you get this slow, you get this oscillation. The difference in the frequencies determines this envelope behavior, and it gets sort of, the envelope gets, as the frequencies get close, that envelope gets smaller, slower, if you will. And so you can really sort of see the wave, but with its changing amplitude. And so you get, if this were a sound, it would be loud and then soft and then loud. So you'd get some tone, sort of average tone between the two frequencies, but it would be loud and then soft and then loud. And when you get to a matching frequency, then they're always at the same, they're not going in and out of phase. They're just staying together. And so then you just get something that is uniformly loud. So, and then if you go to the other side, you get the phenomenon again. So on either, if the frequency match doesn't matter if the second one is higher or lower, you get the same, oscillating amplitude sort of beat phenomenon. But it goes away when you match. So it's a way to, I don't know, tune things to sort of listen for, if you have two sounds, listen for the beats, and then if you're tuning something, if the beats go away, then you have a match. But anyway, I didn't really teach you about beats so much as I wanted to teach you about define a function, plot that function, plot, and these could be completely two different functions. I'm just showing you the same function with different parameters, but I can plot two functions, and I can manipulate a function, sort of leave one of the parameters, not make it a variable, but make it a parameter. Then I can change, or then some, whatever some user can change. Okay, that's what I wanted to show you. Thanks for your attention.